Good afternoon, class. So this is the lecture for, or the video for the September 15th class, and I'm recording this on Sunday, September 13th, and this is the only video for this week since Thursday's class is canceled. So we're going to start off where we left off last time, which is we're discussing how to deposit layers of material, whether they be metals or dielectrics, and where we left off was with physical layer deposition, which is basically either evaporation or sputtering. And what you've learned so far is that sputtering is done by introducing what's called a plasma, or a ionized gas, into the chamber. And that ionized gas, the ions strike the target material, which then gets knocked off and flies off and hits the substrate and deposits your film. And if you notice over here, and I'll try to indicate with the cursor here, it leads us into the next subject, because it talks about how if in a sputterer you introduce certain gases into the plasma, for example oxygen, you can, besides the physical action of sputtering the material to be deposited onto the substrate, you can also cause a chemical reaction to occur at the surface of the substrate. And so, for example, it says here that you can deposit, for example, molecular structures on the surface. And so if you had, for example, a target of tantalum, and you did sputtering in an oxygen atmosphere, you could cause a chemical reaction. So what you actually deposited was not tantalum, but tantalum oxide. And the same thing there, you know, if your target material was titanium, and you put nitrogen gas into the plasma, you could get titanium nitride on the surface instead of titanium. And so, you know, in a sense, sputtering, this is called reactive sputtering. Reactive sputtering sort of leads us into our next subject, which is chemical vapor deposition. And in a chemical vapor deposition, you have various gases present, like silane, that undergo chemical reactions in the, it's still in a plasma, and so when you have these chemical reactions taking place, okay, it can result in molecular structures being deposited. For example, these equations up here, yeah, okay, they've got them grouped together, but basically, if you put SiH4, which is called silane, you can result in silicon reacting with the surface, and so that's a way to deposit silicon. Or you can use silicon tetrachloride to do the same thing. And so basically, at a very high temperature, you can cause these reactions to take place, and you can deposit silicon. You can deposit silicon dioxide, and you can deposit silicon nitride. And particularly silicon nitride is a particularly useful dielectric film in lots of microelectronic devices. And for this, I want you to also view the second clean room video, which is on the deposition of silicon nitride. So, you know, I don't want you to get hung up in these chemical reactions too much. You know, let's just look at this figure here, and basically this figure is showing kind of somewhat schematically the gas flow tends to be more vertical and then off to the side, but you can have flowing gas like this, where the gas, it consists of molecular constituents, and the plasma causes them to undergo a dissociation and a reaction on the surface, so that you can deposit some film. And it's called chemical vapor deposition because it is a chemical reaction that's taking place on the surface, not just a physical, hitting the surface. And a typical there's different types of reactors, and particularly there's what's called LPCVD and PECVD. And what I want you to focus on for this course is what's called PECVD, and that stands for plasma enhanced chemical vapor deposition, it's used primarily for silicon nitride, but basically, this is a schematic, and you'll see what it actually looks like in the clean room video. But basically, this is called the showerhead electrode because the gases flow through it and get ionized in the form of plasma, and then the wafer's down there, and so the constituents basically kind of flow off to the side and back there, and that's how the material is deposited on the surface. And this, it's called plasma enhanced because basically you're introducing not just thermal energy, but RF energy or electromagnetic, like a microwave kind of, only at a different frequency. Usually around 13 megahertz is used to heat up the plasma using RF power. And so, there's all kinds of recipes, and in the clean room video, he goes through the settings, the RF power and various other settings to do this. And now the difference between plasma enhanced chemical vapor deposition and essentially, non-plasma enhanced is LPCVD, where LPCVD stands for, does he have it here? It's low pressure chemical vapor deposition. It's where you're relying upon thermal energy alone. He doesn't do it here. Maybe I missed it. Okay, well, in any event, there's what's called LPCVD, which is, now, they tend to give you different films in the sense that basically PECVD, because it's done in a plasma, you incorporate the material at non-stoichiometric ratios. So, let me get back to the board here. LPCVD, you tend to get silicon nitride, and actually I have to look and see what the numbers are here. Yeah, 3 and 4. This is called stoichiometric. Which basically means it's a molecular structure. This is a molecule of silicon nitride, and the film basically is composed of molecules of silicon nitride. Whereas PECVD, you tend to get, usually it's written SINX, which basically means that X here, okay, the way to think about this is that X equals 0.75 would be stoichiometric, meaning, the other way around, X equal 1.33 ratio 4 to 3 4/3 would be stoichiometric silicon nitride, whereas SINX in PECVD you can vary all over the place, but basically X tends to be around like 0.7, 0.8. And that actually leads to kind of an advantage of PECVD. Well, in a sense, it's maybe not an advantage, but it's a feature or something you can do, which is you can vary this composition of nitride, and that allows you to do kind of two things. So if you, this isn't a course on optics, but much of my work in microelectronics has been in photonic devices, and in particular, I've used silicon nitride as a for its optical properties. And whereas stoichiometric silicon nitride, which has a nitrogen content of 1.33, tends to have a refractive index of about 2. Okay, so N here is the refractive index. If you think about it, X is the composition of nitride, so 1 over that is the composition of silicon. As you add more silicon, okay, N for PECVD can be anywhere from 2 to like even as high as 2.8. And the way to think about that is that when you go to this high, meaning that low of X, its silicon content is much higher, and since silicon has a much higher refractive index than silicon nitride, you can get a higher refractive index. Now, you do pay one aspect of silicon nitride or the PECVD is that you can vary the composition, and whereas for LPCVD it tends to be purely stoichiometric, meaning this ratio of silicon to nitrogen atoms is fixed. Now, so that's nice that you can vary things with the silicon nitride. Unfortunately, it tends to come with a penalty, which is that as you make X much lower, the stress tends to be much higher, and so as you go to higher values of refractive index, you can get what's called cracking. Well, that's what it is, cracking of the silicon nitride film. So, I mean, now you're probably listening here and you're wondering, okay, what do I have to know for the exam? And you know, I mean, I don't want you to focus on these chemical reactions that they have in the book here. As you, for example, watch the video, the clean room video, or as you go into the clean room yourself, you will develop your own recipes. And I'm just trying to give you some advanced knowledge of you know, how you might try to adjust the ratio of things. Okay, so you know, we could just, as I said, we have the clean room video, so that really augments what I'm telling you here about PECVD, and I want you to watch it. Now, when it, you know, so for in this section, you know, I listed, okay. All right, we can do it in this order. So I listed the sections we'd be covering. And the next one is atomic layer deposition. Now, atomic layer deposition is used. What you'll find is that far more of your work in the clean room is with either you know, evaporation or sputtering or CVD, particularly PECVD. Atomic layer deposition is a very specialized deposition process, because it's to a certain extent a chemical process like CVD, but the way to think about it is it's simply sort of been set up that you do it in steps. And for example, you may do a first step where you introduce a gaseous species that deposits one layer of material. And then you introduce a second gas, okay, on top of that first layer that introduces a second layer of, now when I say layer, I mean monolayer, I mean one atom thick. And then the point is that like this step here cannot go beyond one atomic layer, meaning it doesn't matter how much gas you have in here, because of the reaction is specific to the previous cycle in the previous material. You can only deposit one monolayer at a time, as it's shown here. So you have one atom species, the second atom species, the next atom species, and so on and so forth. And so you know, that's just what it sounds like. You can deposit atomic layers, and it's to a certain extent kind of like CVD in the sense that there's a chemical reaction going on. And you know, again, this is the kind of thing, you know, if we could have had more clean room videos, I would have had one showing atomic layer deposition, but it's less used in microelectronic fabrication, and so I simply want you to be aware of it. Now, in the okay, we'll do this one here and then go forward. So I'm looking at the syllabus here, and you should be looking at it also whenever you're thinking about what we're doing in the course. And I just noticed I'm out of focus here, and I apologize for that. So let me see if I can fix that. Okay, I don't want to fool with it anymore now. All right, we're back in focus. Sorry, okay, so that whole discussion, hopefully, of atomic layer deposition, let me go back to this figure. The point is it's a cycle of one type of a monolayer or atomic layer, followed by a second type, followed by the first type again. And so you run the reactor in this sort of two-cycle period and deposit one atomic layer at a time that way. Okay, and finally, so you know, perhaps I can summarize. I'm going to try and avoid being in the video so I don't mess up the focus. So physical layer deposition. Evaporation, sputtering, chemical vapor deposition, particularly plasma-enhanced chemical vapor deposition. And now fourth, okay, maybe I'm going to have to. I think what it is that okay. So that it's a lighting issue. Okay. And the fourth one is electroplating. Okay, I'm going to try and avoid the board here and use. Okay, so in electroplating, let's go to the picture here. It's not, it's not very good drawing because what you would, this would be like in a beaker or something. Basically, you have a liquid solution. For example, cupric sulfate. I think that's how you say that. And so this is a liquid in here, and you have an anode, a metallic anode, and then you have your wafer, which is also connected. And this can be very, it can be sophisticated or relatively unsophisticated. Meaning, you can just have like a little sort of alligator clip holding your wafer and charging it up. And so basically, what happens in here is you apply a voltage between the anode, this metal rod, and this is all in a beaker here, and there's a solution here, and it causes the solution, which is basically an electrolyte, to ionize into copper atoms and sulfide atoms, and then basically this is negatively charged, and it's pretty simple to understand. You put in an electrolyte, a liquid, such that it ionizes into metal atoms that have, and then you use the right signs. For this example, cupric sulfate ionizes into positive copper atoms, and so you negatively charge the wafer, and the copper atoms go flying over and start forming a layer. And this is as the title sort of indicates, is primarily used for metal deposition, plating, and particularly it's a very useful way to produce a very fast, thick film. Meaning, it's something where you can deposit a 10 micron film in a few minutes, basically. So in the material here in the textbook, it teaches you a little bit about that. We don't have a clean room video on electroplating. Electroplating, and also, okay, that's what I was looking for. Gold is done by an electrolyte solution, AuCN. I forget what that is. I mean, I know the chemical. But basically, this disassociates into actual gold ions, and so this is a case where again you would, I guess usually it is the case that you negatively charge the wafer because the metal species is positively charged, and so we didn't really go over, and he kind of, I think in the video, went over evaporation deposition rates, and they tend to be on the order of, you might get 10 angstroms per second or so. 10 angstroms per second would be 600 angstroms per minute, and so that would like be 0.06 microns per minute. So like evaporation and I mean, basically when it comes down to it, you can deposit by evaporation generally in the research lab, or if you can use electroplating. Electroplating, you can get like 10 microns a minute. I mean, you can really plate up really fast. Now, the problems are you can't. I've never used electroplating, for example, on a pattern substrate. I know people that have. I'm not sure how well it works. Because it does tend to, oh, here we go, electroplating on photoresist pattern. See, what happens is that you tend to get overplating above the photoresist, and so you can't perform the liftoff process as easily. Now, one thing you can do, and that's this picture here, is that with electroplating, if you combine an electroplating process where this is photoresist, you first produce a blanket layer, and then you deposit metal structures in the photoresist opening, and you use a back polishing, and then you strip the resist, you can get freestanding metal structures that are very, very thick. Or not freestanding, but just very thick metal structures. And that's a picture of it here. Again, you know, the author of this textbook is MEMS. We've gone over MEMS, sort of more interested in MEMS. And at one point there was a lot of interest in making like gears and stuff on a silicon wafer, so that you can actually have mechanical structures and things like that. And you know, in the commercial world, I don't know where things like gears like that have done anything. I mean, the actual examples of uses of MEMS are things like accelerometers that we've discussed. But I do know of one application that's actually, I mean, if anyone's interested, I can discuss it with them offline. All right, that's mainly what I wanted you to be interested or to, in I won't go up back to the board yet until I have to, and I'll just leave that up and refer to the board that the main physical layer deposition techniques are evaporation, sputtering, chemical vapor deposition, particularly plasma enhanced chemical vapor deposition, and electroplating. Now, in the syllabus, and I'll jump there now, there's a section 7.5 in the textbook. So it's a little bit out of place. All right, where he talks about adhesion. See, up till now, the discussion has been of depositing some layer of a single material, like gold, all right, or silicon dioxide, or something like that. But the reality is that, for example, gold will not adhere very well to silicon. If you try and deposit gold on silicon, it will tend to peel off. And so people have developed recipes for layered structure, and I'm just going to sort of reach my arm in here so I don't change the focus. But for example, a silicon wafer, all right, if you want a gold contact, what you do first is you deposit titanium or chromium. And titanium and chromium stick very well to surfaces. And I guess, you know, I mean, this is one of these things where people know this, and why, for example, titanium and chromium have such good adhesion is, you know, I mean, honestly, I don't know that it is that well understood what the reason for that is. It's not, I mean, adhesion of some thin film you're depositing on the surface is to a certain extent based upon some chemical aspects. But I mean, when you deposit, you know, a metal on silicon, it's not really forming a chemical bond with the silicon. It's sort of stays there through various other types of forces, van der Waals forces or other forces like that. And I guess I'll just say that, you know, titanium particularly tends to be a very hard material, and you know, I guess I've never really understood whether it's because the adhesion is because of actual adhesion, or because the nature of titanium is that it's such a hard material that it simply won't come off. But just continue, and well, in the book here he's saying it's because the titanium forms an oxide with the surface. That could be, I guess, you know, however you need to think about it. The point is, you put a layer of titanium or chromium first, and then you can deposit your gold. And that's how you typically form a contact on a semiconductor. And the titanium, the thickness can be as low as 50 angstroms. So a typical contact would have like 50 angstroms of titanium, and then maybe, you know, like 5,000 angstroms of gold. And then that would form a nice electrode that you could probe or wire bond to, and it would be nice and mechanically robust. I mean, he says here, I mean, his suggestion is 10 nanometers, which is 100 angstroms. I guess a lot of people use 50 because that tends to work, and to a certain extent in semiconductor processing, it's like most other things. You raise the value of something until it works, and then kind of more is not necessarily better. So a lot of people use 50 or 5 nanometers. Let me see what else he says here. There's higher level structures that you can use, but the main thing I wanted you to be aware of is that you usually deposit a structured contact, so that you first deposit an adhesion metal, and then the now you may ask yourself, why not just deposit a bunch of titanium? Well, that is because its surface forms an oxide. So if I tried to make a contact with just titanium, and then I pulled it out of the chamber, it would immediately oxidize in air, forming an insulator on its surface, and so it wouldn't work well for depositing other metals on, or bonding, or probing. And whereas gold, because it's a noble metal, doesn't react, you want to use it as a surface, as what is exposed to the atmosphere. Along these lines, you can use I'll put over here silver. So you know, what I'm saying here is basically that for your contact, if you're making some contact, you put down an adhesion metal, but then you have to cover that with a noble metal. Silver is also so that it doesn't oxidize. Silver is also a noble metal, and it is much cheaper than gold. So for a lot of projects, particularly where you have to have a thick contact, and there's certain applications, certain recipes that call for, like, instead of 5,000 angstroms of the contact metal, as much as 5 microns. And if you think about it, you're using some evaporation source. If you deposit 5 microns of gold, you're going through, you know, $1,000 worth of gold. Whereas if you can do it with silver, silver is roughly these days, I mean, 1% of the cost of gold. Silver goes for, I mean, $20 an ounce, whereas gold can go for $2,000 an ounce. So now the thing is that, okay, silver's not as nice. There's a lot of applications, particularly for solar cells, where people just use silver straight. And they don't worry about this next issue, which is that if you use silver, one thing, silver doesn't form an oxide in air because it's a noble metal, but it will do what's called tarnishing, which is where it reacts with sulfur in the atmosphere to produce a tarnish. If you've ever used actual silverware, meaning knives and forks made out of silver, you'll realize that it can tarnish in the atmosphere, and that's basically a reaction with sulfur in the atmosphere. So sometimes, you know, if you use silver, for example, to make like a layer a few microns thick, what I've done is I've then capped it with a layer of gold, and that's worked fine. So the point here is that what I've found is that if you're going to make a very thick contact, and there's sometimes reasons why you want to do it, you want to put down your adhesion layer, and that adhesion layer can be very thin, 50 angstroms. I mean, 100 angstroms. Once you do 50, it seems like it's enough. I wouldn't recommend doing hundreds of angstroms because that can lead to issues. And then if your metal contact has to be very thick, you can use silver and deposit microns of silver by evaporation. And then to sort of form a nice pristine surface that doesn't oxidize or tarnish, you can then put a few thousand angstrom layer of gold on top of that, and that kind of acts to seal the contact. And the point is that I have found that you don't need another adhesion layer between that the surface of that silver and the top gold layer. Okay, so yeah, you I've rarely done this because, frankly, I mean, if the real, okay, so he's talking about an adhesion test here, and there is an adhesion test, which is to use Scotch tape, which sounds very barbaric, and it is, but you know, that's standard off. That's what people generally refer to as Scotch tape or transparent office tape. If you're interested in you know, how well your thin film material is sticking to the substrate, you can take Scotch tape, you know, adhesive tape, put it down on the surface of the thin film and pull on it relative to the substrate and see if it comes up. I don't kind of know the point of this, meaning that what you usually find is that you know, I mean, depositing the thin film is one process step among many. Sometimes one process step among dozens of process steps. And basically, as you develop a recipe, if the contact survives the subsequent process steps, then you're good. So there's kind of no reason to, in the middle of your process, you know, test and see whether. And in fact, I mean, if you did put Scotch tape on your semiconductor wafer to do that test, you would have to throw that wafer away because it would be contaminated. He goes into some other stuff here that I'm not requiring you to do. Again, there's a lot of oh, okay, that's 7.5. Okay, so yeah, that's the extent that I wanted to discuss with you, and you kind of understand why in this discussion I mixed 7.5 back in the discussion. But let's go back now So the order in the syllabus is now going back to 5.9. And so you can see in the syllabus, I've kind of organized the discussion that sometimes requires you to go back and forth a little bit in the textbook, but not too much. 5.9 is about stress. Which, oh, damn it. Okay. Alrighty. I'm starting to get the hang of this. Okay. I won't try to draw on the board here, but any thin film will develop stress, and stress has two signs. It's basically either compressive or tensile. All right, and you can refer to the figure here. Next page. So, tensile stress is left and compressive stress is right. So the way to think about this is that, and again, I'm going to try and avoid going to the board so that I don't get the focusing issue. Which, by the way, the focusing issue is apparently because when I'm referring to the projector, I have to turn the lights down, and so the autofocus is not as robust. Anyway, getting back to this figure here. This shows what happens when you deposit a thin film on a wafer. Now, he's got sort of an intermediate picture here. I want you to don't think about that. I mean, the easiest way to think about what happens here is that, okay, if I'm under tensile stress, okay, it means, and I don't even like what he's drawn here. So ignore this here, just focus on, okay, the thin film, and this is what happened. So you deposited the thin film on the substrate, you pulled it out of the evaporator or whatever you used to deposit the thin film, and you saw that the wafer bowed like this, and you go, oh my goodness. Now, you wouldn't ever actually see this to this extent, meaning, you know, I mean, if you took it out, if you saw this much bowing, everything would have probably cracked by then. The bowing is usually on the order of maybe 10 microns across a 2 or 3 inch wafer. And so in order to see this, it's not that much. You kind of have to put it under the microscope and observe that, you know, when you lay it on the platen, in fact, the sides are up higher than the bottom, which you can see with a depth of focus type experiment. There are also instruments in the laboratory that allow you to image such a bowing, and it's usually on the order. I mean, a bowing of 100. Well, a bowing of 10 microns is a lot of bowing. Now, I want you to focus on this figure here, and what I want you to think about is, okay, if I'm under tensile stress, imagine you're the thin film, and you're stuck to the substrate. And tensile stress means that you're pulling in on yourself, okay? It's like I'm under tension, and tension basically means it's like the thin film, once it's deposited, tries to make itself smaller. And so if the thin film is trying to make itself smaller, that's why I don't like this intermediate picture, because that's kind of opposite what's going on. The thin film is trying to make itself smaller, and it causes it then pulls up the side of the wafer like this. And whereas in compressive stress, it's like the thin film is trying to make itself bigger, and so it pushes down on the side like that. So I mean that's okay. This is tension. This is tensile. This is compressive stress. Now, why does this happen? Well, it's actually kind of complicated why it happens. There's a way that it could happen, and it is related to your homework problem, and maybe we'll discuss it more in the chat class. But one way that it can happen is that you deposit the thin film at a very high temperature. Okay, let's say 400 degrees, and you then cool down the sample, and there's something called the coefficient of thermal expansion, which is basically how much materials expand when elevated in temperature. And if the coefficient of thermal expansion of the thin film is higher than the substrate, upon cooling down, it will pull in on itself, and it will be tensile. Whereas if the coefficient of thermal expansion of the thin film is lower than the substrate, then it'll compressively stress like that. Now that sounds like a nice explanation. It's unfortunately not really true. It's an easy way to think about why thin films have stresses. The actual reason is, let me see what he says here. I think he has the right answer here. Well, he does talk about thermal expansion. That's not the right answer. The right answer is, he has over here, voids. Okay. When you deposit a thin film, particularly by evaporation, you incorporate some gas atoms, for example. Or the voids could simply be, vacuum. Meaning, like the metal is coming down. I'm not going to try and draw the picture here, but I'm just going to say in words. The metal is coming down, and it's not perfectly uniform all the way across, and there's voids in it. And so what happens is that any material doesn't like having voids, and what will happen is those voids will try to leave the film, basically either going up to the surface or to the sides even. And when those voids leave the film, the rest of the film has to move into place to fill the vacuum, so to speak, of what's left over. And so the incorporation of voids will result naturally in tensile stress, and what he says here is true. Evaporated metal films are typically under tensile stress, and so this is what you usually get with a metal film. Now, the homework problem is basically, okay, if that happened, and thinking about the coefficient of thermal expansion, what would happen if you raised the temperature? And so I want you to think about that in terms of, okay, if I pulled my sample out with a thin film and it looked like that, what would happen if I changed the temperature? So that was the homework problem there. Okay, so that's stresses in thin films, and it's to a certain extent. I mean, he shows you can make devices using the stress. That's again his MEMS coming over. You can do stress measurements. Now, I don't want you to worry about this equation here. In fact, I've done stress measurements. I usually do it optically. All right, and he has a discussion about different kinds of metal thin films. I guess here, Here he talks about adhesion layers. But I guess I didn't need to go up to 7.5. But besides adhesion layers and conductors, meaning electrodes, and there's optical materials, as we've discussed, particularly things like anti-reflection coatings and stuff like that. Besides what we've discussed, there's contacts. Now, this is where semiconductor physics and semiconductor fabrication sort of intersect again. And the problem here is that, okay, I can't discuss with you what, okay, so you're saying here, which is true, there's what's called ohmic contacts and there's Schottky contacts, which if you know semiconductor physics is a little bit of a misnomer. But, you know, I can't, basically a Schottky contact is where, for whatever reason, a straight metal like titanium gold makes a good ohmic contact. And you know, without going into semiconductor physics, I can't tell you kind of why that's true. But typically, in order to make an ohmic contact, you use a dopant in the metal itself. So for example, aluminum, think about it, is a group 3 material. Okay, here I will write this down. All right, I stayed in focus. Aluminum is group 3, so it's naturally a p-type dopant. It's not one you typically use, but it will work, and so you will get a good ohmic contact to p-type silicon. So if you're making a semiconductor device in silicon, particularly where the top surface is p-type silicon, a good way to make an ohmic contact is to use aluminum. Aluminum is a very interesting material in a lot of respects. There are whole textbooks devoted to aluminum. Aluminum is also a pretty good adhesive material. Not always. Certainly for some types of substrates, you don't rely upon its adhesion. You use other materials like titanium and chromium. But on silicon, it's a pretty good adherent material, and so aluminum can be a very convenient material to use because a lot of times you don't need an adhesion layer, and it also makes an ohmic contact to p-type material, and it's because it itself is a p-type dopant. So I wanted to point that out about that a lot of time you're trying to deposit an actual ohmic contact to a semiconductor device. Now you will notice, which I don't think I have the slide here, but when we looked at NAM's evaporator, if you remember, the material he had in the thermal pocket was gold germanium, and that's because for gallium arsenide, germanium is an N-type dopant. So anyway, I mean, I want you to just generally be aware of the fact. I don't want you to try to memorize, because I mean, memorizing all the different types of ohmic contact material, but what I want you to sort of understand in general is if you're making a contact to a semiconductor, it's very useful to use a metal that contains dopant atoms for the particular type, N or P. And if anyone's interested, I can give you a list of good metals for different types of uh, semiconductor contacts. This is basically a kind of table you would find for different metals giving the resistivity. This is the coefficient of thermal expansion. And this is a useful thing to know too, the thermal conductivity. Sometimes when you're making devices, you not only want to use the metal contacts as an electrical contact, but as a thermal via. And what this shows is that it doesn't have silver. It's listing copper as 4 watts per centimeter. That's a little bit on the high side. For some reason, silver is not listed. Silver tends to have the highest thermal conductivity, or gold. And what you see here is that things like titanium, and that's the other reason why you may not want to make it so thick, it has a very poor thermal conductivity. And then over here is the melting point, and what you see most striking is that aluminum has a very low melting point. And so sometimes you do have to worry about that. Because, for example, if you use an aluminum contact on a semiconductor device that has subsequent processing steps that are up around 500 centigrade, this is going to be a problem. So, this is a useful chart to have. Now, bonding pads. I have extensive experience in wire bonding to semiconductor devices. It does have special requirements, but basically it's still just a tie-gold system. If anyone wants any knowledge of what to do for a wire bond pad ever, they can ask me. All right, then other thin films, polysilicon is typically used. Now, CVD tends to give you polysilicon, which means it's crystalline with different grains. You can get amorphous silicon, which is purely amorphous like glass, and it's useful for some applications. But the usual dielectrics you're interested in are oxides and nitrides. We've talked about PECVD versus LPCVD, and the fact that silicon nitride tends to, under PECVD, you can adjust the ratio of silicon to nitrogen. And other things to understand here are what's called passivation. What passivation means is it's a coating for a semiconductor device that reduces the defects at the surface. And so silicon nitride, particularly oxynitride, tends to be used there. Again, we're touching on semiconductor physics. You can make capacitors with dielectrics between, you can make a capacitor on a integrated circuit. Honestly, I've used silicon monoxide for that, and it works very well. Here are some different properties of silicon dioxide and silicon nitride. Of course, the resistivity it's an insulator. The main thing you see here is that the thermal conductivity is very low compared to metals, especially for silicon dioxide. And here it shows the refractive index for silicon nitride, and that is for stoichiometric silicon nitride with a 3:4 ratio. If you make it silicon rich through PECVD, you can raise that refractive index to about 2.8, really, almost. And beyond that, I don't want you to worry about this too much. Now, the textbook is really interesting and has a lot of interesting stuff, but you know, we have limited time, and so you know, you may find it interesting to read about polymer films and things like that. There are a lot of neat applications. You can, I mean, essentially, it's putting plastic down on an integrated circuit, and so you know, this is fun reading. But what is covered by any exams is the syllabus itself. All right, now, what we just talked about with physical layer deposition, evaporation, sputtering, CVD, certainly electroplating, they produce what's called either polycrystalline or amorphous films, meaning that it's not a single crystal. Epitaxy produces a single crystal, and you may have heard I'm looking for it here, molecular beam epitaxy. Right now, I'm going to try and not screw up my focus, but we'll see what I can do here. So, physical layer deposition results in polycrystalline or amorphous but sometimes we want to deposit an actual single crystal. Okay, so we have a layer, we have a substrate, and it has a lattice constant, you know, meaning it's a single crystal, and we want to deposit a layer which, let's see if we can draw bigger atoms, okay, where so this is the substrate, and this is the quote-unquote thin film. And so, if this is crystalline, if this is a single crystal, we call that epitaxy. And we're sort of, you know, the video is getting a little bit on the long side. I don't like going much over an hour for these single class videos because there's too much to cover then in the chat class. And so there's two types. There's what's called molecular beam epitaxy. Epitaxy, or MBE. And then, where does he have it here? Okay, and like he says here, molecular beam epitaxy is a variation of evaporation. It's just, you know, doing evaporation in a very specialized fashion. And so you can get single crystal layers like he has shown here. And the other way is, well, CVD, but particularly I thought he had it here somewhere. Okay. Maybe it's earlier. Okay, well, oh, here we go. It was right here. Or there's MOVPE, which stands for metal organic CVD. Now, what's the point of the metal organic here? Well, by using a precursor with a metal like gallium, so if you had this chemical, and so it's basically CVD like we've discussed, but using gases like gallium tetrachloride allows you to deposit gallium on the surface, and then if you do it with arsenic, ASH3, I'm not sure what that's called, you can deposit gallium arsenide. Okay, and so that's why you use a metal organic. It just means that these are metal organics because gallium or arsenic by themselves are metals. And so there's the two types. Molecular beam epitaxy (MBE) is far more used in research environments, and MOVPE CVD is far more used in manufacturing environments. And perhaps we can discuss more. All right, we're kind of have to end here, and I may discuss this in the chat class because the next homework involves this diagram. So this is sort of the Bible when it comes to, I'm out of focus. There we go, it came back. This is sort of our Bible when it comes to epitaxy, because what this shows is the x-axis is the lattice constant, and the y-axis is the band gap. And frequently, when you're performing epitaxy, it's to put one type of material on top of another type of material, meaning one band gap on top of another band gap. And since you don't necessarily, taking this course, know what a band gap is, that's a little bit complicated to understand. But the point is that there are lots of particularly optoelectronic devices based upon stacking epitaxial layers of, for example, gallium arsenide and aluminum arsenide. Now, the thing I wanted to point out here, and maybe we can have a further discussion on it in the chat class, is that besides these compounds or elements of semiconductor layers, there are alloys, and in particular, there's one particular alloy here where my hand is. All right, and these lines represent. Oh, this is strange. Okay. This is indium arsenide. I don't know why it is connected here. Never noticed that. Okay, here's indium arsenide, and here's gallium arsenide. All right, and so besides and the point is that, okay, if I'm depositing on, for example, indium phosphide, all right, and I'm going to do this in a sequence here. So its lattice constant A is equal to, and you can kind of read it off the chart there, about 0.582 or so, 0.583 angstroms. All right, now, if I try to deposit gallium arsenide, Okay, its lattice constant you can kind of read off there is 0.56 32 or something like that. All right, now you can do this. You can deposit now. You see, the lattice constants don't match up, and so what's going to happen is that this layer of gallium arsenide, as you deposit it, is going to be under what's called strain, because it doesn't want to be at this lattice constant. It will be forced to be at that lattice constant because you're depositing it on the indium phosphide. All right, but what will happen is that if you try to deposit more than, I don't know, 10 angstroms of it, the crystal will crack. All right, and so it won't work beyond a certain point. All right, so what if we tried indium arsenide? Now its lattice constant you can read off of there is like 0.63. All right, same thing. Okay, they don't match, right? So it's not going to be happy trying to grow on here. That won't work. So what do? You make what's called an alloy. All right, and you deposit indium gallium arsenide. And if you adjust X right, all right, and that's what's meant by these lines going between. So it's not gallium arsenide, it's an indium arsenide, but it's an alloy between it. And if you adjust X right, okay, for a particular X, for X equal to 0.52, if my memory is correct, meaning you're depositing a crystal that's 52% indium and 48% gallium, then A matches. Okay? And so you can deposit elements by epitaxy, you can deposit compounds, or you can deposit alloys, which are, now the thing is, this is still a single crystal. It's just that, you know, if you looked at the lattice, if you looked at 100 lattices, not exactly because, you know, more than one, but you would see indium in some sites, some lattice sites, and gallium in other lattice sites, such that their ratio was 0.52. Then the lattice constant would match. And so that's a very important principle to know in epitaxy. All right, we're going to leave it there for today, and because it's already an hour and 13 minutes. All right, and I'll talk to you during the chat class.